Welcome to this lecture on methods in biostatistics. Today, we are going to explore one of the most powerful tools in a scientist's toolkit, the chi-square test. Imagine you buy a bag of candies, and the manufacturer claims exactly half are red and half are blue. But when you open it, you count 60 red and 40 blue. Is the company lying, or is it just random chance? This is the exact kind of real-world puzzle the chi-square test is designed to solve. Let us dive in and see how it works. Now that we have our candy puzzle in mind, let us understand what this test actually does. The chi-square test acts as a mathematical lie detector. In biology and medicine, we often have a theoretical expectation of what should happen, but real-world data is messy. By comparing what we actually observe against what we expected to see, this test measures the gap between our expectations and reality. If that gap is too large, it tells us that our initial theory might be wrong. This allows researchers to make confident, objective scientific decisions, instead of just relying on gut feelings or guessing. Building on that idea of comparing expectations to reality, it is important to know exactly what kind of data we are dealing with. The chi-square test is a non-parametric tool used specifically for categorical data. This means information that can be sorted into distinct buckets or groups, such as blood types, eye colors, or whether a patient was cured or not cured. Unlike other statistical tests that look at averages, the chi-square test strictly looks at raw counts or tallies. Without this tool, we would have no objective way to validate Gregor Mendel's genetic theories or prove if a new vaccine genuinely works better than a placebo. So, how do we actually measure this gap mathematically? This brings us to the fundamental formula of the chi-square test. Conceptually, we need to calculate the total error across all our categories. We take the observed frequency, O sub I, and subtract the expected frequency, E sub I. We square this difference so that positive and negative errors do not cancel each other out. Then, we divide by the expected value to standardize the error. Finally, the Greek letter sigma tells us to add up these standardized errors for every single category. The result is our chi-square statistic. If your observed values are very close to your expected values, this final score will be very small. But if they are vastly different, the score grows larger, strongly suggesting your initial hypothesis was incorrect. Before we can interpret that final chi-square score, we must understand a crucial concept called degrees of freedom. Think of degrees of freedom like the number of choices you have before the final outcome is mathematically forced. For example, if you know you have 100 total patients, divided into two categories, cured and not cured, and I tell you 60 were cured, you automatically know that 40 were not cured. I do not even have to say it. Because only one category was free to vary before the other was locked in, we say there is 1 degree of freedom. This concept adjusts our expectations so that experiments with many categories are judged fairly compared to those with only a few. Now that we grasp the intuition behind degrees of freedom, let us look at its mathematical form. The formula is beautifully simple. df equals k minus 1. Here, the variable k represents the total number of distinct categories or groups in your experiment. By subtracting 1 from the total number of categories, we find the exact number of independent pieces of information that went into calculating our statistic. As the number of categories increases, the degrees of freedom also increases. This physically changes the shape of the distribution curve we use to judge our final score. It is a small formula, but absolutely essential for finding our p-value and making a valid scientific conclusion. With our formulas ready, let us walk through a classic biological example known as a goodness of fit test. Suppose a botanist is crossing pea plants. According to Mendelian genetics, the offspring should have yellow and green seeds in a strict 3-to-1 ratio. The botanist grows 100 plants. Before looking at the real data, we must calculate our theoretical baseline. Since the expected ratio is 3-to-1, 3 out of every 4 plants should be yellow. We multiply 100 by 3/4 to get 75 expected yellow seeds. Similarly, we multiply 100 by 1/4 to get 25 expected green seeds. These numbers represent a perfect, idealized world without any random variation. Now we bring in our messy, real-world data. The botanist actually counted 85 yellow seeds and 15 green seeds. We apply our main chi-square formula by looking at both categories simultaneously. For the yellow seeds, we take our observed 85, subtract the expected 75, square the result, and divide by 75. We do the exact same process for the green seeds. Squaring the differences ensures the positive error from the yellow seeds does not cancel out the negative error from the green seeds. Adding these together gives us a final chi-square statistic of 5.33. Since our degrees of freedom is 1, the critical threshold is 3.84. Because 5.33 is larger, we reject the idea that this deviation happened by chance. The plants are significantly deviating from the theory. Let us level up to a highly practical example used constantly in medical research, the test of independence. Imagine a clinical trial testing a new drug for a skin rash on 200 patients. 100 get the real drug, and 100 get a placebo. In the drug group, 70 are cured. In the placebo group, 50 are cured. Did the drug actually cause the higher cure rate? To solve this, we first figure out what the data would look like if the drug had absolutely zero effect. We find the overall cure rate by adding all 120 cured patients and dividing by the 200 total patients. This gives us an overall cure rate of 60%. This combined rate represents our null hypothesis, assuming the treatment does nothing special. Using that overall 60% cure rate, we can now build our expected frequencies. We take the 100 patients who received the drug and multiply by 0.60. This tells us that if the drug is completely ineffective, we should expect exactly 60 patients in this group to heal naturally. By the exact same logic, we apply the 60% rate to the 100 placebo patients, giving us 60 expected natural healings there as well. Since each group has 100 people, this leaves 40 patients expected to not heal in each of the two groups. We now have our perfect zero-effect baseline ready for comparison. We now apply the chi-square formula across all 4 possible outcomes. For each bucket, we take the observed count, subtract the expected count, square the difference, and divide by the expected count. This massive sum captures the total deviation of the entire clinical trial from our zero-effect baseline. By adding all 4 fractions together, we get 1.67 plus 2.5 plus 1.67 plus 2.5. Our final calculated chi-square statistic is 8.34. For a 2x2 table, the degrees of freedom is 1, making our critical value 3.84. Since 8.34 is much larger, we strongly reject the idea that the drug and the cure rate are independent. The new drug genuinely works. To truly understand what that final number means, let us look at the chi-square distribution curve. The horizontal axis represents the possible chi-square values, and the vertical axis shows the probability of getting that value by pure random chance. Notice the vertical dashed line at 3.84? This is our critical threshold for 1 degree of freedom. The red shaded area to the right is the rejection region. If our calculated score falls in this red zone, the probability of it happening by chance is less than 5%. As you can see, our calculated score of 8.34 falls deep inside this rejection region. This visual proves why we can confidently declare that our biological hypothesis holds true in the real world. We have covered a lot of ground today. To summarize, the chi-square test is an indispensable statistical tool that allows us to compare observed categorical data against theoretical expectations. By squaring the differences between what we see and what we expect and standardizing them, we generate a single score that represents the total deviation in our experiment. We also learned how degrees of freedom ensure our experiments are judged fairly. Whether you are verifying the laws of genetics or proving the efficacy of a life-saving drug, this test provides the mathematical rigor needed to separate genuine scientific discoveries from random statistical noise. Mastering this concept empowers you to look at raw counts and confidently uncover the truth.